Okay, so let us continue with our study of logic programming. And we had mentioned briefly that uh, Prolog is implementation of what we can now say an approximation to logic programming. In pure logic programming, you have to specify only the relations, and the rest can be left to the inference engine, which will somehow figure out which rules to apply to which facts and so on and so forth. So, as an example of what can be a pure logic program, which basically focuses on the relation, we can try to define a sort, a program to sort, let us say numbers. So, we can say that sort x y, and by this we mean y is a sorted permutation of x. The semantics of sort x y is that we have two lists, one of them is x and one of them is y, and y is a sorted permutation of x essentially. So, if you wanted to run this program, for example, you would say goal, for example, sort 3 2 1, let us say 3 y, and it would say yes if y is equal to 1 2 3, for example, if you are sorting in ascending order. So, you could give that the first argument is unsorted array, and the second argument which the program will find for you is a sorted array essentially. We can define this sort in a very simple fashion by saying, by just sort of rewriting the definition that I have written in as a logic program, and we can say that that find a permutation y of x and test whether it is sorted or not. So, this is trying to sort of get at the basic idea of why did people think of logic programming. Essentially, their goal was that as a programmer or as a user, you should be able to focus on the relations between input and output, and not so much on the procedural control of what is the next operation that I must carry out and things like that. So, you should focus on specifying the relation. So, if you want to write a program to sort this thing, you should say, okay, what do you mean by sorting? You mean by sorting that you find a permutation which is sorted essentially. Then you have to of course define what do you mean by sorted and so on. So, how do you define sorted? For example, you could say sorted, an empty list is sorted. Then you could say let me use this square bracket notation. You could say that a list with one element is sorted by definition, but if it is a longer list, and I will use this notation or let me use the old notation. or maybe this one was better, I think. This notation basically is a short form for Kahn's notation. So, x is the head of the list and y is the second element of the list and z is the rest of the list essentially. So, the rightmost element is the rest of the list and this is the head, and recursively you can say between y and z, y is the head and z is the rest essentially. So, initially this is a rest and so on essentially. So, anyway, so the basic idea is that you can define what do you mean by sorted by saying that a list which has at least 2 elements is sorted if x is less than y. Let us say we have this and this ordering between elements defined already, if x is less than y, and sorted the rest of the list which is made up of y comma z, which recursively will look at the next 2 elements and so on and so forth. So, essentially what you are saying is that a list is sorted if the first element is less than the second element and the rest of the list is sorted recursively essentially. So, which again will look at the second and the third element and see that second is less than the third element, then third is less than the fourth element, and eventually it will boil down to one of the 2 base clauses and the program will terminate essentially. The first clause is just for the sake of completeness, you are looking at empty list also. So, we have defined, or let us assume that we can define what is sorted, but what about defining permutation? So, you need to define that as well. So, you could define permutation by saying that something like this, that a list which starts with x and goes and the rest is y is a permutation of a list which starts with v and goes to u, provided I write a function predicate called remove x from this list u v z and the meaning of this is if I remove x from u v. So, this element x must be present somewhere in u v. If I remove it from u v, then I get z and y is a permutation of z. So, I am not writing the base clause, you can write the base clause which says that an empty list is a permutation of itself. Let us write it here. That is the base clause. This clause which defines the permutation says that if I have 2 lists, one of them is beginning with an x and the other one is beginning with u and v something, then if I remove from the second list x and whatever remains I call as z, then that z must be a permutation of y. So, essentially I have removed the first element from the. So, I am saying that u v is a permutation of x y if I remove x from u v, and whatever remains is a permutation of y essentially. So, of course, this x will be somewhere inside u v, and this remove itself you can define by saying that remove, if it happens to be the first element, then just return the rest of the list. So, that is the base clause for remove, and the recursive clause would be that look inside V for x essentially. Remove x from u V will give me a list which I can call as u comma z, provided if I remove from V x from V to give z essentially. So, this remove is also a two recursive program. The base clause says that if it is at the head, you can simply remove it. If it is not at the head, you must look inside the rest of the list to remove it essentially. So, in any case, what we have seen here is that you can write a logic program to sort a list, and sorting, as we know, is an activity which is one of the most common activities in the industry, that most of the time programs in industry are spent on sorting essentially. Now, if you were to use this program that we just wrote, I mean you could translate this into Prolog quite straightforward manner, but you can see that it is as inefficient a program as it can get essentially, because what is it saying? It is saying look for a permutation of a list and see whether it is sorted. Now, obviously, that does not make sense at all, because the number of permutations of a list are very many, and it has its own way of plodding through all the permutations and then doing that essentially. So, obviously, one does not want to write pure logic programs, we want to write programs in Prolog which are efficient essentially. And as an exercise, I will ask you to write merge sort and quick sort in logic programming, and you can see that all you have to do is to define by what is a merge sort. Basically, a merge sort x, if you say that y is a merge sorted version of x, then you are going to say that I am going to break up x into two parts, let us call them x 1 and x 2. That you will have to define logically what do you mean by breaking up. And of course, most of the time we say left half of the array and right half of the array, but it does not really matter. You could simply say I will take the alternate elements from x. So, I will take the first element and put it in x 1, the second element in x 2, the third element in x 1 again, the fourth element in x 2. You could just separate the elements in any manner, break it down into smaller problems, recursively merge sort the two arrays x 1 and x 2, and then append the two outputs to give you the sort of thing. So, you can write that as a logic program, and I will leave this as a small exercise. I want to focus on some other things, which is again to do with efficiency, and let us say to avoid useless search. How can we, since we are working with a deterministic strategy, we are trying to optimize our program so that they will run well in Prolog. Let us see how we can avoid some useless search essentially. So, let us work again with an example to illustrate the idea. So, we will say that two people are incompatible, which I will just use I, x y. I keep forgetting to write the question marks. So, maybe we should consistently write them, but I hope you will be able to make sense of it even without that. if let us say hobby x h x and technical h x. This is an example I have taken from Charniak and McDermott book. So, first to understand this definition, what this definition is saying that two people x and y are incompatible if x has a hobby which is technical. So, let us say by technical we mean things like having interest in mobile phones and computers and motorcycles and things like that essentially. And if y has a hobby which is not technical. So, let us say non technical means let us say watching movies or listening to music or something like that, it does not matter. Let us say we just have two kinds of hobbies, one is technical kind and one is not technical kind, and this definition is saying that two people are hobby if one of them has a technical hobby and the other one has a non technical hobby essentially. Now, let us say we are talking about John and Mary, and let us for argument's sake that both of them have the same hobbies, computers, mobiles, mobikes. What else is a technical hobby? Can you just tell me something? Okay, whatever. Let us say there are some set of technical hobbies. Now, obviously, if you were to ask a query, are John and Mary incompatible? The answer should be no. So, essentially what we are saying is all hobbies of both are technical. So, I am not listing them out. So, if we ask this query that are John and Mary incompatible, we will have to show that find a hobby for John, whatever the hobby is, show that hobby is technical, find a hobby for Mary, and show that it is not technical. We will at some point see how to define this not essentially. So, we try this essentially. So, first we try with computers and we find that it is technical. Then we go to find hobby of Mary and we try computers and find that it is not technical. So, I will put a cross to say that it is not technical, or in other words not technical is false essentially, because it is also technical, computers is technical. Then I will try for Mary mobiles and find that it is not technical, then find mobikes is not technical, and if there are only these three hobbies, then you have to backtrack. So, Prolog will backtrack. What will it do? It will now go and say try mobiles. But if you now look at this problem a little bit, you can see that when you looked at John's hobby, which is computers, you tried all of Mary's hobbies and you could not find a non technical hobby essentially. Now, what is the point of coming back and trying another hobby of John, which is mobiles, because again you will find all the hobbies of Mary are non technical essentially. So, this work is useless. And Prolog gives you a mechanism for the programmer to signal that do not try this again essentially. How do we do that? In Prolog, there is a statement called cut, which is denoted by an exclamation mark, and so a cut goal is a goal which is satisfied trivially, but it basically controls the procedural behavior of Prolog essentially. So, if I were to put a cut here, what this is saying is that after you have satisfied the first goal and after you have satisfied the second goal, which is you have found a hobby for John and you have found that it is technical, the entire truth value of the incompatibility goal will depend upon the remaining two goals. So, in a sense the program can backtrack between the third and the fourth goals. It can try one hobby for Mary and try to see whether it is not technical, then try another hobby and so on, but it cannot backtrack across the cut essentially. So, a cut is like a one way gate essentially, or it is like what you might say a Lakshman Rekha essentially. Once you go on the other side, you cannot come back essentially. And if you have failed to satisfy the third and the fourth goals in this case, which means you have failed to find a hobby for Mary which is not technical, do not try to satisfy the incompatibility goal again. The incompatibility goal is going to fail essentially. So, this is the basic idea of cut, and it is useful in many places in making a program efficient essentially. So, let me at this point introduce this negation by failure. Not good. So, this is in some sense adding to the semantics of Prolog, and so for example, not technical H y, we had this goal in the previous example, where this not is what we are talking about. What is this not essentially? So, negation by failure says if one cannot show G to be true, then not G is true. Okay, now there is a subtle difference between logical negation and negation by failure. Logical negation says that not G is true. When you say in logical negation, when you say not G is true, you are essentially saying that G is false essentially. In negation by failure, which is a property of a language like Prolog, when you say not G is true, you are showing that I am not able to show that G is true essentially. So, it is a failure to show that G is true essentially. So, we can define negation by failure as follows. So, first you try to show that G is true, If you can show that G is true, then you use the cut here. So, remember that we had talked about the cut, and maybe we will talk about the cut a little bit more in the next class as well. And then fail essentially. Fail means evaluate to false. So, fail is a constant predicate, it is like false, it is stating false essentially. So, we are saying that not G is true, if you can show G to be true, if G is true, which means here this is what we are saying, right. If G is true, then you will proceed further to the next sub goal. Then go through the cut which we have put there, and the next thing is return false. In other words, whenever G is true, this predicate not G will return false, and that is what happened in the John and Mary example we saw. Mary had these 3 hobbies: computers, mobiles and motorbikes, and every time we tried to see whether they are not technical, it returned as failure, because each of them was technical. Computers was classified as a technical hobby, mobile was classified as a technical hobby. If you just look at this program again, we had sort of we had stated here that all hobbies of both are technical, computers are technical, this thing, and you were trying to show that you were trying to find a non technical hobby of Mary, and every time you tried, you found that computers were technical. So, not G returns false, not tech returns false, mobiles were technical. So, not mobiles returns false, mobiles were technical. So, not mobiles returns false. So, if you can show the goal to be true, then you return false, otherwise you return this. Without any condition. So, it is like a fact essentially, which means it is true essentially. So, this is a definition of negation by failure. It is basically 2 clauses, and notice that we are talking prologue, which means order matters essentially. If you had put not G first, then you would always return not G, but now because prologue looks at things in a particular order, it will first try the first clause essentially. First clause says try to show that G is true. If it fails to show that G is true, then it will backtrack and come to the second clause and say yes, not G is true. But if it succeeds in showing that G is true, it will go through the cut and return false essentially. So, not G will return false essentially. So, not G will be returned true only when you fail to show that G is true essentially. So, a couple of examples of statements that use the cut, and we will probably look at it again later. So, you can define a number to be composite if the number is greater than 1 and not So, if you have a definition for prime numbers already, then you can use that definition to define a composite number, and you are defining a composite number by saying that a number n is composite if it is greater than 1 and it is not a prime essentially. So, that is a definition. And maybe you should say greater than 2, I think. But 1 is enough, because because 2 is anyway a prime. So, 2 will not be returned as a composite, 3 will not be returned as a composite, but 4 will be returned as a composite number essentially. Another example is you can say that x has no children if it is not the case that if x is not a parent of someone. One has to be a little bit careful here. This example has been given in one of our textbooks, which is Brackman and Levesque. So, you must go and read it up there, but you must be careful that the reading of this is that there does not exist y that y is a existentially quantified variable in this case. Most of these formulas that we are talking about are universally quantified. Remember that our notation here, but when the formula occurs on the right hand side inside the knot, it is treated as an existential variable essentially. So, the reading of the sentence is x has no children if there does not exist a y such that x is a parent of y. It is not, the reading is not that for all y x is not a parent of y. It simply says that there is no y such that x is a parent of y. One has to be a little bit careful. Okay, so, we will stop here. In the next class, we will start by looking at cut a little bit more, because it is a very useful mechanism in Prolog, and then we will try to see try to compare forward chaining and backward chaining, and try to see whether they are adequate for us or whether they have some problem essentially. We will see that both forward chaining and backward chaining are not complete essentially, and we will move towards the resolution method, which is a complete method essentially. And then from there we come back to backward chaining and see that backward chaining is actually a special case of resolution method, which is more efficient essentially, efficient but not complete.